Hello everyone, my name is Emil, and today I'll be presenting instant neural graphics primitives with a multi-resolution hash encoding. This paper was published by NVIDIA employees, actually, NVIDIA researchers. It's actually quite an interesting paper, and the reason why I chose this paper because it has promising applications. And so the potential for its applications is actually quite more interesting, kind of, its inner workings actually. So let's go over it and let's see what it is. So the contents are basically this. This is what I will be presenting. I will first introduce you what is going on here, and second, I'll talk about the applications, potential applications, and then I'll talk about previous work. And finally, I will try to explain like what is the core innovation behind this work. So basically, why did it make a difference, basically? Let's proceed. So imagine that you take, let's say, 16 to 30 images from different angles for this particular building, and you're given a task for reconstructing a 3D image of it, right? Let's say mesh, right? Could be anything, I mean, doesn't matter. And the requirement is, let's say that you have right about enough, let's say, 100 images, right? Doesn't really matter, but all of them are from different angles. And you need to like reconstruct a smooth, like perfect 3D representation of it. Basically, we need to be able to scroll it from side to side, and we need to be able to kind of see a smooth transition as we slide, and we have to be able to like see the sides of it and behind it and so forth. So basically, as you can see, like from these two images, like here it is taken from the input. You can see that it's taken from this side, and the output is also from this side, right? So this is the kind of close representation to the input. And in the second one, we just scroll to the other side, and this was the input photo from our collection, and this is how it rendered. As you can see in here, right, so around here, it kind of messed up, but overall, it kind of did a good job in kind of reconstructing the whole thing. And the reason it messed up, I think, because we have taken multiple photos from different angles, sometimes lighting got in the way, and on the one picture, it was kind of more brighter than the other pictures, so it couldn't learn this particular place. So maybe that's why it looks like this. So let me introduce this neural radiance field. So this was also a paper published in actually 2020. The paper that I'm presenting today, multi-resolution hash encoding, it's actually has been published in 2022. And basically what NERF does is it takes input images. I'm sorry for the poor image quality here, but what we have right here is like 100 images of this, basically drums, but taken from different angles, and then NERF optimizes it, using neural networks, and then it creates a 3D representation of it. So basically, this is what we've got. And it made a big news for a while because it was very effective. Basically, the quality of this high dimensional reconstruction was very high. So let's see how NERF accomplished this first. Basically, what we have here is deep neural network, and it takes 5D input and it outputs a volume density and the color density. So what are those? So basically, input is just XYZ, the coordinates. It's theta and phi, and what theta and phi represent, those are basically just angles, view directions, basically, right? So from which angle are you looking at it? So basically, it's basically view direction, and the output is volume density. And what volume density is basically, it transfers if at some, let's say, location, if something exists there, essentially, right? So let's say that you have 3D image, and at any particular location, you want to know what we have there, right? Essentially, and it's only a function of location, because what we have somewhere does not depend on the direction, right? Either we have it or we don't, so it's a function of location. And the color density, however, depends on both location and the view direction, because if you look at an object from different angles, but because of the lighting, because of the distance, right, the color may change. So basically, we both need direction and we need location. So the way that that the neural network works is that essentially it takes 100 images and it tries to overfit them essentially. So this is intentional overfitting basically. And one way that it does it is, suppose that you have you have the view direction, let's say like right here, right, as you can see. So basically you emit a light ray in one direction and you basically look at each points right here, right? So this is just a graph of what this is. So it goes on and here it encounters something. And then here it says, okay, there's nothing. This is just an empty space, right? So we first find nothing and then we find something and then once again, nothing, right? So this is basically what volume density means. And the color is pretty much, you know, the color. And the way that this is optimized is let's say you start from random, like let's say you start from scratch, and then you basically calculate L2 loss from, you know, from your actual images, right, to your, let's say, recreated 3D output, right? Because you have multiple images, you can actually calculate this rendering loss by taking your actual images as reference. So let's proceed. So let's see, let's first actually discuss what the problems with this is. So the thing is, this is actually high quality, this actually has high quality performance. Just the problem is that it takes too long to train it because it's deep neural network, and the rendering time is actually, I mean, in days, not just in hours, but actually in days. It takes 1 to 2 days to actually get the output. And you even get this performance on a very powerful GPU. So it's not just a typical GPU. Even on powerful GPU, it takes like a couple of days to actually get the output. What this Instant-NGP did, basically, this multi-resolution hash encoding, is that it first it decreased the processing time. It greatly reduced the processing time, and it did not have to sacrifice any quality from basically. So let's see what the inner workings of this Instant-NGP basically is, right? So this is kind of the whole architecture essentially. As you can see, we do not have a deep neural network here. We only have 2 hidden layer neural networks. So the reason why it's so fast, and we'll get to the speed part as well. So the reason why it's so fast is because this is not deep neural network, right? It only has 2 hidden layers. But then how does it optimize the parameters, right? So how does it check the parameters? How does it reach the, let's say, comparable performance? So the way that they do it essentially is the only difference between their job, right, and the previous NERF is essentially about how you represent the spatial data. So basically, it's all about parametric encoding, right? So the way that they do it is using hash tables. So they use multiple hash tables for different resolutions, and they essentially update when they apply back propagation. They not only update the neural network's parameters, but they also update the future parameters that are in the hash table as well. So basically, instead of representing the whole thing as voxels, they using linear interpolation, they just embed them inside of a hash table. And then from hash table, they provide the whole thing as an input to the neural network itself. So because the whole thing is differentiable, backpropagation can be applied to the hash table, to the entries in the hash tables as well. So basically, as neural network updates, the entries in the hash table update as well. And with this, they kind of reduce the processing time. So let's go forward. So this is actually the result. So basically, NERF's processing time was in 30 hours, right? So basically, For some, it was 32, 34, like 36. So 30 hours compared to 30 seconds. So basically what multi-resolution hashing achieved is that it reduced from 30 hours to 30 seconds. So this is a very huge deal. And let's I forgot to talk about the applications as well. So because it has very high performance in terms of quality and speed, you can write many different software applications for it, right? So let's say today we have different hardware for 3D scanners, but with this, you don't even need 3D scanners. You can just take multiple pictures, and let's say you take 16 pictures, and from 16 pictures, you generate kind of high quality 3D mockup, right? 3D model. That's one thing. And for example, for entertainment industry, what they can do is usually working to create 3D models. What they instead could do is to just draw 2D pictures and then create 3D models based on that. So it can have a huge improvement for gaming industry as well. And you can also create multiple different type of augmented reality or virtual reality applications for it. And the best part is it's actually open source. You can see the code, you can edit it, you can run it on your own software. I wanted to show the demo actually because I knew that the whole thing is open source. It's just that unfortunately my computer's GPU is actually not so good. And so yeah, I checked the videos of people who run it, and they complained only about the GPU because their GPU was not good enough. They will not be able to recreate kind of high quality image. So yeah, that's it. I hope you enjoyed it.